Okay guys, so now we're going to talk about oxidative phosphorylation. So these are just the products of what we've seen thus far from glycolysis, turning pyruvate to acetyl-CoA, and then the TCA cycle. We've gotten 2 ATP and 2 NADH from glycolysis. That's just net, right? Because it costs us some to make it. In this transfer, we got 2 NADH and 2 carbon dioxides. And then here we got 2 NADH, 2 FADH, 2, that should be a 2. And then 2 GTP, which can be seen as 2 ATP, and then 4 carbon dioxides, okay? So I'm gonna try to explain this messy picture for you guys. And then we'll kind of summarize everything. So on this side is the intermembrane space. On this side is the mitochondrial matrix. So in complex 1, we have the NADHs, and they turn into the NAD plus, and they pump protons through. They also, it's very faint for my brown colored, but it goes through and it donates these 2 electrons to COQ. And I'll talk about COQ after I get through the second one. So the second complex donates the FADH2, and so it doesn't donate anything. It transfers electrons. So we get FADH and then 2 hydrogen ions. And then we have these 2 electrons, and they also get put into this COQ. So what is COQ? It's also called like COQ10. There's like supplements that you can buy to take it. But it's a non-protein molecule that accepts electrons from complex 1 and 2. So what it does is that will end up reacting with complex 3. So COQ reacts with complex 3. So complex 3 requires iron, and what we have to do is we have to change the ionization of iron. And what does it? Well, it's COQ that transfers those electrons, and that allows for those extra 2 hydrogens that we've pumped off. It allows them to go through complex 3, okay? So 1 pushes hydrogens through, 2 does not. It is part of electrons, and then 3, we have some protons that can finally pump through it. Okay, so in the meanwhile, we still have protons pumping through. And so from 3, we have 4 electrons that go to the site C. And site C is a protein. So COQ is not a protein. Site C is a protein. And what it does is it transfers electrons from complex 3 to complex 4. And I'll explain. I want to go back one sec. I missed something in complex 2. Complex 2 is also the same thing as succinate dehydrogenase. And that was when, in the TCA cycle, we have this FAD, and we're transferring to FADH2. So in the process, we go from succinate to fumarate. Same exact thing. Just a quick note for that. But anyway, so coming back, we go from 3 to 4. And so in the process, 4 requires iron and copper to drive the formation of water. And during this process, protons are pumped into the intermembrane space. So we have iron and copper here, and it just causes the hydrogens and oxygens to be pumped through, and that we're left over with water, and we have lots of hydrogen on this side now, on the intermembrane side. So we've gone through 1 through 4. So an important note is 1 through 4 is the electron transport chain. Number 5 is ATP synthase, and the entire thing 1 through 5 is oxidative phosphorylation. Okay, so we'll wrap this up real quick. Due to the electrochemical gradient coupled with ATP synthetase, it causes the synthesis of ATP. There's an image that you should probably look up in the notes. So this F of 0 or O, whatever you want to call it, it turns the gamma head. And so we have this F of 0, and we have a gamma head below. And what it does is it starts to turn, and so it causes that gamma piece to turn. And the gamma piece is located inside of this F1 piece. And so the F1 piece, it stays stationary, so it doesn't move. But because the gamma piece is moving inside it, the subunit pairs off with the F1 piece, and it allows it to phosphorylate ADP to ATP. And that's where you get all your energy from. Okay, so in summary, I'm gonna hop over here. We have glycolysis. We get a net of 2 ATP and 2 NADHs. In the pyruvate to acetyl-CoA, we get 2 NADHs. And then from TCA, we get 6 NADHs, 2 FADH2s, and 2 GTPs. Something to note is that this is for 1 molecule of glucose, and we know that we have a splitting phase, so we get 2 pyruvates. And because we have 2 pyruvates, we get 2 acetyl-CoAs. So for every 2 acetyl-CoAs that enter the TCA, this is what we get. If it was only 1 pyruvate, this number would be divided in half. But because it's normally not that case, that's why we go about this way. So for ATP, you just multiply it by 1 because we're trying to calculate the net ATP. For NADHs, we can multiply by 2.5, so we get 5. Again, 5. And then 6 times 2.5 is 15. And then FADH, we actually multiply by 1.5. So it doesn't give us quite as much energy, but we get a 3 from it. And then GTP, we act it as if it was ATP, so we get 2. So the sum is 32, okay? So this wraps up the entire pathways of glycolysis, TCA cycle, and then oxidative phosphorylation.